Hello, in this lecture we will find out the length of chord AB. In the drawing we have a semicircle, and inside this semicircle we have three circles. The small two circles are identical, and actually the center of the semicircle is at point O, and we know that the diameter of the semicircle PQ equals to 8 units, and the diameter is twice as large as the radius. So if the diameter equals to 8 units, then the radius of the semicircle will be equal to 4 units. So that is to say, PO, that is the radius of this semicircle, will be equal to 4 units. And OQ will be also equal, that is the radius of the semicircle will be equal to 4 units. And actually point C is the center of the middle circle, and therefore OX is also the diameter of the middle circle, and it is also the radius of this semicircle. So OX equals to 4 units in its size, and the diameter OX equals to 4 units, so the radius will be equal half of the diameter, that is to say CX, that is the radius of the middle circle, will be equal half of 4 units, that is to say it will be equal to 2 units, and the radius OC will be also equal to 2 units, that is half of 4 units. And actually we have the small circle is tangent to the middle circle. At this point we will define the touching point between the two circles as point Y, and the distance between the centers of two circles with an external launch point between them will be equal to the sum of their radiuses. So if we will define the center of this small circle as point M, and the radius of this small circle will be defined as R, and we know that the radius of this middle circle equals to 2 units. So in total, the distance between the centers of those two circles will be equal to R plus 2. That is the sum of their radiuses. Okay, then we will define the touching point between PQ and the small circle as point N. Then we will join points M and N together by a straight line. Actually, MN is the radius of the small circle, so we have the radius R of the small circle that is drawn to the point of tangency, that is to say it is drawn to point N, that is the point of tangency of tangent PQ with this small circle. Therefore the tangent PQ will be perpendicular to this radius, that is to say this angle will be equal to 90 degrees, and this angle also will be equal to 90 degrees, because a tangent to a circle is perpendicular to the radius drawn to its points of tangency. This radius, the radius MN, it is drawn to the point of tangency, therefore the tangent PQ will be perpendicular to this radius, that is to say this angle will be equal to 90 degrees and this angle also will be equal to 90 degrees. Likewise, here we have this radius, the radius of the middle circle, or CO. It is drawn to the point of tangency, that is to say it is drawn to point O, that is the point of tangency between tangent PQ and this middle circle. Therefore, the tangent PQ will be perpendicular to this radius, that is to say this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees. Okay, then we will draw perpendicular from point M to CO. So, and we will define the touching point between the perpendicular to CO as point D. So this angle equals to 90 degrees and this angle will be also equal to 90 degrees. So I will draw again this quadrilateral. I will draw it again in order to be more clear. Actually, we have points N, O, M, that is the radius, and we have point D. So I drew again the quadrilateral MNOC. Actually, if we focus on quadrilateral MDNO, we have in this quadrilateral 3 right angles, 1, 2, 3. And we know that the sum of the angles in any quadrilateral equals to 360 degrees. So if we focus on quadrilateral MNOD, then so in quadrilateral MNOD, we know that the sum of the angles in any quadrilateral equals to 360 degrees. Therefore, in quadrilateral MNOD, the sum of its angles must be equal to 360 degrees. That is to say, the 3 right angles, that they are, the total sum of them is 90 degrees times 3, that is to say it equals to 270 degrees, plus the size of this angle. We will define it as angle X plus the size of angle X must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral equals to 360 degrees. So I will repeat again. The sum of the angles in this quadrilateral MNOD must be equal to 360 degrees, that is to say 270 degrees plus the size of angle x must be equal to 360 degrees. Okay, so here we will subtract from this equality 270 degrees, so and we will get that the size of angle x equals to 360 degrees minus 270 degrees, it equals to 90 degrees. So we actually found out that the fourth angle, this angle x, it is also a right angle, that is to say it equals to 90 degrees in its size. Therefore, we have quadrilateral MNOD that has 4 right angles. And any quadrilateral with 4 right angles must be at least a rectangle if not a square. So quadrilateral MNOD is at least a rectangle if not a square. I will repeat again. Quadrilateral MNOD is at least a rectangle if not a square. Okay, and we know that the opposite sides of a rectangle are equal to each other. That is to say, side MN of rectangle MNOD equals to side OD. Those two sides are equal to each other, and we know that MN equals to the radius of the small circle. Therefore, OD will be also equal to the radius of the small circle. That is to say, it equals to R. Okay? And so we know also that CO this line segment CO is the radius of this middle circle. CO is the radius of this middle circle, that is to say it equals to 2 units. So CO equals to 2 units because it is the radius of the middle circle. Okay, so CO equals to 2 units. CO equals to 2 units, so we will write here that CO equals to 2 units and OD equals to R. So CD, you can see here CD equals to CO minus OD. Again, CD equals to CO minus OD. That is to say, CD equals to CO, that is 2 units, minus OD, that is R. So in total, CD equals to 2 minus R. CD equals to 2 minus R. So here we will focus on the right triangle, triangle MDC. And on the right triangle, triangle MDC, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, MC squared, the hypotenuse squared, will be equal to the sum of the squares of the perpendiculars, will be equal to CD squared plus MD squared. I will repeat again according to the Pythagoras theorem. According to the Pythagoras theorem, in the right triangle, triangle CDM, the square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say, MC square equals to CD square plus MD square. Okay, but what is the size of MC? The size of MC is R plus 2. MC equals to R plus 2. MC equals to R plus 2, so MC square will be equal to R plus 2 square. And it equals to CD square. CD square, CD equals to 2 minus R, so CD square will be equal to 2 minus R square plus MD square. So in total we got that R plus 2 square equals to 2 minus R square plus MD square. Here we will open the brackets in both sides of equation number 1, and we will get that R plus 2 square equals to R square plus 4 plus 4R, and it equals to 2 minus R square. 2 minus R square equals to 4 plus R square minus 4R plus MD square. So in total, after we open the brackets in equation number 1, we got this expression. So here we have R square in both sides of the equation, so R square will get cancelled, and we have 4 on both sides of the equation, so 4 will be also cancelled. So in total we get that here 4 equals to 4, here we have R square plus 4 equals to minus 4R. So it is actually, we will add, actually 4 is cancelled, here 4 is cancelled, so it is actually not 4R is cancelled, but 4 is cancelled, so we have here 4R is not cancelled, but 4 is cancelled, so we have here 4R minus 4R, so we will add 4R to this equation number 1, and we will get that (4R plus 4R) is 8R. 8R equals to MD square. So we got that for 8R equals to MD square. Here we will take a root out of equation number 1, and we will get that MD equals to the square root of 8R. Actually 8R is 4 times, 8 is 4 times 2, so we will substitute 8 by 4 times 2 times R. and the square root of 4 is 2, so we will get that MD equals to the square root of 4 is 2, 2 times square root of 2R. So we actually found out that MD equals to 2 times square root of 2R. So we can write here in the drawing that MD equals to 2 times square root of 2R. Okay? But because of the fact that the opposite sides of a rectangle are equal to each other, therefore MD will be equal to NO, but we know that MD equals to 2 times square root of 2R, so NO that equals to MD will be also equal to 2 times square root of 2R. Okay? So, in the next step, we will join together points M and O by a straight line. We join together points M and O by a straight line. We know that MA, it is actually the radius of the small circle, that is to say it equals to R, and AO, it is the radius of the semicircle, that is to say it equals to 4. Therefore, MO will be equal to the radius of the semicircle, that is to say to 4 minus AM. That is to say MO equals to 4 minus R. Okay, so here we also join together points M and O by a straight line. We have already found out that MO equals to 4 minus R. So we will focus on the right triangle, triangle MNO. Okay? We will focus on this right triangle, triangle MNO, the green triangle, triangle MNO. So in the right green triangle, triangle MNO, we know that in the right triangle, triangle MNO, the right green triangle, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So that is to say MO square, that is the square of the hypotenuse, equals to MN square plus NO square. I will repeat again. In the right green triangle, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, the square of the hypotenuse is MO square, and MO square equals to the sum of the squares of the perpendiculars. That is to say, it equals to MN square plus NO square. But we have already found out that MO equals to 4 minus R. MO equals to 4 minus R, therefore MO squared will be equal to 4 minus R squared. And it equals to Mn squared. Mn is the radius of the small circle, so Mn squared will be equal to R squared plus NO squared. NO equals to 2 times square root of 2R, so NO squared will be equal to 2 times square root of 2R squared. 2 times square root of 2R squared. So in total we got that 4 minus R squared equals to R squared plus square root of 2 times square root of 2R squared. Here we will open the brackets in both sides of the equation, and we will get that, equation number 2, and we will get that 4 minus R squared is 16 plus R squared minus 8R, and it equals to R squared. 2 times square root of 2R squared is 8R. So here, in total, we got this expression for equation number 2. Here we have R squared on both sides of the equation, so R squared will get cancelled. We will add to this equation 8R, and we will get that according to equation number 2, 16 equals to 16R, because 8R plus 8R is 16R. So here we will divide equation number 2, here this equation, by 16, and we will get that the radius of the small circle R equals to 1 unit. So we found out that the radius of the small circle R equals to 1 unit. So we actually can write here it equals to R equals to 1 unit, and here the radius equals to 1 unit, the radius of the small circle. Here also R equals to 1 unit. So in the next step, we know that PQ is parallel to AB. It is given us in the question, and we have a rule that states that corresponding angles between parallel lines are equal to each other. I'll write it down. According to the rule that states that corresponding angles between parallel lines are equal to each other, corresponding angles between parallel lines are equal to each other. Again, it is given us the question that AB is parallel to PQ. AB is parallel to PQ. So because of the fact that AB is parallel to PQ, those two corresponding angles will be equal to each other, and we know that this angle equals to 90 degrees, so this angle will be also equal to 90 degrees. I'll repeat again. AB is parallel to PQ, therefore those two corresponding angles will be equal to each other, and we know that this angle is a right angle, so therefore those two corresponding angles are equal to each other, and this angle equals to 90 degrees, therefore this angle will be also equal to 90 degrees. So we will define this point as point E, and in the next step we will prove the triangle D, the triangle CEY is similar to the right triangle. The right triangle CEY is similar to the right triangle CDM. Okay? We'll prove that the right triangle CEY is similar to the right triangle CDM. So actually I will show it here. This point is point E, and this point is point Y. So we will prove that the right triangle, this angle equals to 90 degrees. We will prove that the right triangle CEY is similar to the right triangle CDM. Again, we will prove that the green triangle CEY, green right triangle CEY is similar to the right triangle CDM. This triangle CDM. Okay? So, first of all, we have the two right angles. So, angle CEY in triangle CEY equals to angle CDM in triangle CDM, and they are both right angles, they are equal to 90 degrees. I'll repeat again. Angle CEY in triangle CEY equals to angle CDM in triangle CDM. They are both right angles, they are equal to 90 degrees. Those two angles are both right angles, they are equal to 90 degrees, therefore they are equal to each other. And we also have this angle, angle C. It is a common angle, it belongs to both triangles, it belongs to the common angle C belongs to the green triangle, and it is also belongs to the bigger triangle, triangle CDM. So we can write down that angle C equals to angle C is a common angle that belongs to both triangles. I will repeat again. Angle C equals to angle C is a common angle that belongs to both triangles. And the third angle, those two angles are also equal to each other. Those two angles are also equal to each other according to third angle theorem. So angle CYE, angle CYE, this angle is equal to angle CMD, this angle, according to third angle theorem. According to third angle theorem. I will repeat again. Angle CEY equals to angle CMD according to third angle theorem. So those two angles are equal to each other according to third angle theorem. What is third angle theorem? Third angle theorem states that if you have two angles in one triangle that congruent to two angles in another triangle, then the third pair of angles must also congruent. Okay? Therefore, those two angles are equal to each other according to third angle theorem. So we actually proved that all three angles of the green triangle are congruent to all three angles of the triangle CDM. Therefore, we proved that those two triangles similar to each other according to angle similarity rule. So I'll write it down. We actually proved that triangle CEY is similar this is the sign of similar to triangle CDM according to angle similarity rule. I will repeat again. We proved the triangle CEY is similar to triangle CDM according to angle similarity rule. So what is angle similarity rule? Angle similarity rule is that if you prove that all angles in one triangle congruent to all three angles of another triangle, then you prove that those two triangles are similar to each other according to angle similarity rule. And from the fact that triangle CEY is similar to triangle CDM, we will conclude that CE over CY CE over CY in triangle CEY equals to CD over CM in triangle CDM. CD over CM in triangle CDM. I'll repeat again, from the fact that triangle CEY is similar to triangle CDM, we will conclude that CE over CY in triangle CEY is equal to CD over CM in triangle CDM. Okay, but what is the value of CE? The value of CE you can see CE equals to 2 minus R. Here it is written 2 minus R. It is 2 minus R actually. So you can see from the drawing that CE equals to 2 minus R because OC equals to 2 units and CDO equals to R, so CO equals to 2 units and EO and OD equals to R, therefore CD equals to 2 minus R actually. This is actually CD, so CE equals to here CE, so we will leave it as it is. It is CE over CY, and CY you can see from the drawing that CY here CY equals to 2 units. It is the radius of the middle circle, therefore it equals to 2 units, so it is CY equals to 2. And CD, here you can see CD equals to CO, that is 2 units, minus DO, that is R, and that is R, so it is 2 minus R. Again, CD equals to CO minus DO. That is to say, it equals to CO, that is 2 units, minus DO, that is R. So it is actually 2 minus R. Again, CD equals to CO minus DO. CD equals to CO minus DO. So CO is 2 units and DO is R. So it equals to 2 minus R. And CM, you can see here that CM equals to R plus 2. R plus 2. So in total, we got that CE over 2 equals to 2 minus R over R plus 2. But we have already found out that R equals to 1 unit. So 2 minus R, that is 1, and R is 1, so R is 1 and 1 plus 2 is 3, so in total we will get that 2 minus R is 1 because R equals to 1, and R plus 2 is 1 plus 2, that is 3. So in total we got that CE over 2 equals to 1 over 3. Again, CE over 2 equals to 1 over 3, we will multiply equation number 3 by 2, and we will get that CE equals to 2 over 3. Again, we multiply equation number 3 by 2, and we got that CE equals to 2 times 1 over 3 is 2/3. CE equals to 2/3. So we can write here CE equals to 2/3 and CD equals to 1. Again, CD equals to 1 and CE equals to 2/3. You can see from the drawing that DE, ED equals to CD minus CE. DE equals to CD minus CE. Again, CE equals to 2/3 and CD equals to 1. But DE here DE, this small line segment, ED or DE equals to CD, that is 1, minus CE, that is 2/3. So DE in total equals to CD minus CE, or DE equals to CD, that is 1 unit, minus CE, that is 2/3. 1 minus 2/3 is 1/3. So we found out that DE equals to 1/3. DE equals to 1/3. DE equals to 1/3. We can write here that DE equals to 1/3. And actually CE equals to 2/3. Here CE equals to 2/3. So in total, here you can see from the drawing that OE equals to OD, that is 1, plus DE, that is 1/3. Or in other words, OE equals to OD, that is 1 unit, plus DE, that is 1/3. Okay? OE equals to OD plus DE, and OD is the radius of the small circle, it is 1. It is 1 plus DE, that is 1/3, or OE equals to 4/3. OE equals to 4/3. OE equals to 4/3. OE equals to 4/3. So in the next step, we'll join together points O and B by a straight line. BO is the radius of the semicircle, it equals to 4 units. So I draw again triangle OEB, triangle EBO, it is actually this triangle. So this is triangle EBO. I will prove the triangle EBO is a right triangle. Why triangle EBO is a right triangle? Because we have a rule that states that the corresponding angles between parallel lines are equal to each other. We know that AB, line AB is parallel to PQ according to what is given us in the question. And angle, this angle equals to 90 degrees, so those two angles that are equal to each other will be also equal to 90 degrees. So those two angles are right angles, and this angle will be also equal to 90 degrees according to the rule that the sum of the angles on one side of a straight line equals to 180 degrees. Okay, so here this angle equals to 90 degrees. So the sum of the angles at point E, at one side of point E, must be equal to 180 degrees. And we have one angle that equals to 90 degrees, so this angle must also equals to 90 degrees because it must complete the sum of the angles at one side of point E to 180 degrees. Therefore, this angle must be also equal to 90 degrees. That is to say, we actually proved that this angle is a right angle. Therefore, triangle EOB is a right triangle. Triangle EOB is a right triangle. The hypotenuse of the right triangle, triangle EOB, equals to 4 units because the hypotenuse is the radius of the semicircle that equals to 4 units. We have already found out that OE equals to 3 over 4 units. And we will find out the value of EB according to the Pythagoras theorem. According to the Pythagoras theorem, the length of EB will be equal to OB squared. The sum of the squares of the perpendiculars equals to the square of the hypotenuse. That is to say, OB squared will be equal to the sum of the squares of the perpendiculars. That is to say, OB squared that is the square of the hypotenuse, will be equal to the sum of the squares of the perpendiculars. That is to say, will be equal to OE squared plus EB squared. So I will repeat again. In the right triangle OEB, the square of the hypotenuse, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say, OB square equals to OE square plus EB square. Okay? The square of the hypotenuse is OB square, and it equals to the sum of the squares of the perpendiculars, that is to say, it equals to OE square plus EB square. Okay? So, OB equals to 4 units. OB equals to 4 units, therefore OB square is 4 square, 4 square is 16. OE is 4 over 3, so OE square will be equal to 4 over 3 squared plus EB squared. Okay? So we found out that 16 equals to 4 over 3 square plus EB square. 4 over 3 square is 16 over 9. So I'll write it down. (16) equals to 16 over 9 plus EB square. So 4 over 3 square equals to 16 over 9. So in total we got that 16 equals to 16 over 9 plus EB square. We will subtract 16 over 9 from this equation number 4, and we will get that 16 minus 16 over 9 equals to EB square. We subtracted 16 over 9 from this equation. We got that 16 minus 16 over 9 equals to EB square. Here we will multiply 16 by 9 and then we'll divide it by 9 in order to have a common factor with this 16 over 9, and we will get that 16 times 9 over 9 minus 16 equals to EB square. Again, we multiplied 16 by 9 and then we divided by 9 in order to have a common factor with 16 over 9, and we got that 16 times 9 over 9 minus 16 equals to EB square. So here 16 times 9 minus 16 is 16 times 8. So we write it down. So we got that, according to equation number 4, 16 times 8 over 9 equals to EB square. We got that 16 times 8 over 9 equals to EB square. 16 is 8 times 2, so I write it down. So here I substituted 16 by 8 times 2, and we got this expression. We will take a root out of equation number 4, and we will get that EB equals to the square root of 8 times 8 times 2 over 9. So we got that EB equals to the square root of 8 times 8 times 2 over 9. The square root of 8 times 8 is 8, and the square root of 9 is 3. So I write it down. We actually got that EB equals to 8 over 3 times square root of 2. So we found out that the length of EB, it is actually 8 over 3 times square root of 2 units. Okay? So in the next step, we will focus on those two right triangles. So actually I will draw it again in order to see it clearly, because here it is too small. I will draw the two right triangles that will prove that they are congruent to each other. So we actually prove that those two right triangles can go into each other. The triangle AOE is congruent to triangle OBE. Okay? We will prove that the right triangle OEA is congruent to the right triangle OEB. We prove that those two right triangles can go into each other. So first of all, we know that AE equals to EB equals to 4 units. It is actually AB. No, it is, this is O and this is E. OB. So here we know that OB, it is the radius of the semicircle, and it equals to OA. It is also the radius of the semicircle, and they are both equal to 4 units. So those two sides that are the hypotenuse of those two right triangles are equal to each other. They are both equal to 4 units. And we have this side, it is a common side, it belongs to both triangles. So OE is equals to OE. It is a common side that belongs to both triangles. Okay? OE equals to OE. It is a common side that belongs to both triangles. Again, OE equals to OE is a common side that belongs to both triangles. So we actually proved that triangle AOE, this triangle, is congruent to triangle OEB, this triangle. So we proved that those two triangles can go into each other according to the rule that if you have two triangles with a hypotenuse and perpendicular that are equal to each other, then both those two triangles will be congruent to each other. So I write it down. So triangle AOE is congruent to triangle OEB according to the rule that if the hypotenuse and the perpendicular are congruent in two right triangles, then the right triangles, congruent to each other. So I'll read again. We proved that triangle AOE is congruent to triangle OEB according to the rule that if the hypotenuse and the perpendicular are congruent in two right triangles, then the right triangles congruent to each other. Okay, we actually proved that the hypotenuse and a perpendicular in those two right triangles congruent to each other. Therefore, we proved that those two triangles congruent to each other. And from the fact that those two triangles congruent to each other, we will conclude that AE equals to EB. We will conclude that AE equals to EB. AE equals to EB. according to the rule that corresponding sides in congruent triangles are equal to each other. I repeat again. AE equals to EB according to the rule that corresponding sides in congruent triangles are equal to each other. AE equals to EB. But as you can see from the drawing, AB, what is the value of AB? AB equals to AE plus EB. AB equals to AE plus EB. But we know that we already found out that AE equals to EB. So AB equals to AE plus EB, that is to say it equals to EB plus EB. It is to say it equals to 2 times EB. So I'll repeat again. AB equals to AE plus EB. But we know that AE equals to EB, so we can substitute AE by EB. In total we will get that AB equals to EB plus EB. That is to say EB equals to 2 times EB. And we have already found out that EB equals to 8/3 times square root of 2 units. EB equals to 8/3 times square root of 2 units. Okay. EB equals to, we have already found out that EB equals to 8/3 times square root of 2 units. Or AB equals to 2 times 8/3 times square root of 2 units. So AB equals to 2 times 8 is 16/3 times square root of 2 units. AB equals to 16/3 times square root of 2 units. Or in terms of numbers, it equals to 7.54 units. So we actually found out that the length of AB equals to 16/3 times square root of 2 units. So in terms of numbers, the length of chord AB equals to 7.54 units. I will repeat again. Actually, here we found out that the length of chord AB, this chord, equals to either 16/3 times square root of 2 units, or in terms of numbers, the length of chord AB equals to 7.54 units. Okay, the length of this chord AB equals to 7.54 units. Okay, so now I will summarize the lecture. Actually, we wanted to find out the length of this chord AB, and we have here a semicircle, and inside this semicircle we have 3 circles. Those 2 small circles are identical, and the middle circle is tangent to this semicircle at its center, at the center of the semicircle, that is to say it is tangent at point O, that is the center of the semicircle, and it is also, the middle circle also tangent to the semicircle at point X, and OX is a line segment that passes through point C, that is the center of the middle circle. I will repeat again. CX, line segment OX, this line segment, it passes through the center of this middle circle, that is to say it passes through point C, that is the center of this middle circle. Okay? Then we also joined the center of those 2 circles by a straight line, and the length of CM, that is the distance between the radiuses of those 2 circles, equals to the sum of their radiuses, that is to say it equals to R plus 2. R is the radius of the small circle and 2 is the radius of this middle circle, so R plus 2 is the distance between the centers of those circles, so MC equals to R plus 2. Then we actually joined points M and N together by a straight line. Actually, this radius is drawn to the point of tendency, that is to say it is drawn to point M. Therefore, this angle equals to 90 degrees and this angle is equal to 90 degrees. Likewise, this radius CO, is drawn to the point of tendency, that is to say it is drawn to point O, that is the point of tendency with tangent PQ and this middle circle. Therefore, this angle equals to 90 degrees and this angle also equals to 90 degrees. Then we actually also, from point M, we draw perpendicular to CO. So this angle equals to 90 degrees and this angle also equals to 90 degrees. And because of the fact that AB is parallel to PQ, we have the rule that the corresponding angles between parallel lines are equal to each other. That is to say those 2 angles are equal to each other, and this angle equals to 90 degrees, so this angle also equals to 90 degrees. Therefore, actually triangle CEY, this triangle is a right angle. Okay, and here I draw actually the triangle, the quadrilateral C. I draw this quadrilateral again. So if you relate to quadrilateral MN and DO, this quadrilateral, in this quadrilateral we have 3 right angles, 1, 2, 3, and we know that the sum of the angles in any quadrilateral equals to 180 degrees. Therefore, the sum of those two free right angles is 270 degrees plus the size of the fourth angle, that is to say plus angle x, equals to 360 degrees. So in quadrilateral MNOD, 270 degrees plus x equals to 360 degrees, according to the rule that the sum of the angles in any quadrilateral equals to 360 degrees. Here is subtracted 270 degrees from this equality, and we got that angle x equals to 360 degrees minus 270 degrees is 90 degrees. So this angle is a right angle. Therefore, this quadrilateral MDON has 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So quadrilateral MNOQ is at least a rectangle, and in a rectangle we know that the opposite sides are equal to each other, that is to say MN equals to DO, and we know that MN is the radius of the small circle, therefore it equals to R, so DO will be also equal to R because of the fact that the opposite sides of a rectangle are equal to each other. And we related to the right triangle CMD. In this right triangle, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, the square of the hypotenuse is MC square, and it equals to CD square plus MD square. We know that MC equals to R plus 2, that is the distance between the centers of the two circles. It is R plus 2, MC equals to R plus 2, so MC square equals to R plus 2 square. CD equals to 2 minus R. CD equals to 2 minus R. So CD square will be equal to 2 minus R square plus MD square. So we open the brackets in equation number 1, and we got that R plus 2 square equals to R square plus 4R, and it equals to 2 minus R square. 2 minus R square is 4 plus R square minus 4R plus MD square. Okay, plus MD square. Here we have R square on both sides of the equation, so R square will get cancelled, and we have also 4 on both sides of equation number 1, so 4 will get cancelled. In total we got that 4R equals to minus 4R plus dm square or md square. We added 4R to this equation number 1, and we got that according to equation number 1, 4R plus 4R is 8R, and so we got that 8R equals to MD square. So here we took a root from equation number 1, and we got that MD equals to the square root of 8R. MD equals to the square root of 8R, but we know that 8 equals to 4 times 2. So we substituted 8 by 4 times 2, and we got that MD equals to the square root of 4 times 2R, and the square root of 4 is 2. So in total we got that MD equals to 2 times square root of 2R. MD equals to, according to equation number 1, MD equals to 2 times square root of 2R. Okay, then in the next step we actually related to focus on triangle MNO, that is a right triangle. triangle MNO is a right triangle because it has one angle that equals to 90 degrees, therefore the green triangle is a right triangle. And according to the Pythagoras theorem, in the right triangle MNO, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, MO square will be equal to MN square plus NO square. MO square in the right triangle MNO, MO square equals to MN square plus NO square. MN square equals to MO square. The hypotenuse squared equals to MN square plus NO square in the right triangle MNO according to equation number 2. But we know that MO equals to MO equals to 4 minus R. MO, the hypotenuse, equals to 4 minus R. So MO square will be equal to 4 minus R square. MN is the radius, so MN square will be equal to R square. And we have already found out that NO equals to 2 times square root of 2R. Why? Because we have already found out that MD equals to 2 times square root of 2R. And the opposite sides of a rectangle are equal to each other. So if MD equals to 2 times square root of 2R, NO will be also equal to 2 times square root of 2R. So NO equals to 2 times square root of 2R, and NO square will be equal to 2 times square root of 2R squared. So we open the bracket in this side of equation number 2, and we got that 4 minus R square equals to 16 plus R square minus 8R, and it equals to R squared, and 2 times square root of 2R square is 8R. So here we have R square in both sides of equation number 2, so R square will get cancelled. And what is left after we cancelled R square? What is left? It is actually, here we added 8R to this equation number 2, and we got that 16 equals to 8R plus 8R is 16R. So we got that according to equation number 2, 16 equals to 16R. We divided equation number 2 by 16, and we found out that the radius of the small circle R equals to 1 unit. The radius of the small circle R equals to 1 unit. Then we actually found out that those we have here a right triangle. This triangle is a right triangle according to the rule that actually those two angles, because of the fact that MD is parallel to NO, those two angles are also equal to each other, and if this angle is a right angle, this angle is also a right angle, therefore this is a right angle, therefore triangle CMD is a right triangle according to the rule that corresponding angles between parallel lines are equal to each other. Okay? Then we actually proved that triangle CEY, that is a right triangle, is similar to triangle CDM, that is also a right triangle. We proved that those two triangles are similar to each other. Why? First of all, they have two right angles that, of course, are equal to each other. Those two angles are both right angles, and they are equal to each other. So angle CEY equals to angle CDM equals to 90 degrees. And also we have angle C that equals to angle C. It is a common angle. This angle, angle C, is a common angle. It belongs to both triangles. So we can write down that angle C equals to angle C. It's a common angle that belongs to both triangles. Angle C equals to angle C. And those two angles are also equal to each other according to third angle theorem. therefore, that is to say angle CEY equals to angle CMD according to third angle theorem. What is third angle theorem? Third angle theorem states that if two angles in one triangle congruent to two angles in another triangle, then those two triangles are similar to each other according to third angle theorem. Okay, so those two angles are also equal to each other according to third angle theorem. We actually proved that all three angles of the right triangle, triangle CEY, congruent to all three angles of the right triangle, triangle CDM. Therefore, we actually proved that triangle CEY, the green triangle, is similar to triangle CDM, this triangle, according to angle similarity rule. We proved that triangle CEY is similar to triangle CDM according to angle similarity rule. So what is angle similarity rule? Angle similarity rule is that if you prove that all angles in one triangle congruent to all the angles of another triangle, then we proved that those two triangles are similar to each other according to angle similarity rule. And from the fact that the two triangles, triangle CEY is similar to triangle CDM, we will conclude that CE over CY in triangle CEY equals to CD over CM in triangle CDM. Okay, so CE over CY. We know that CY equals to 2 units. Why CY equals to 2 units? Because it is actually the radius of the middle circle, and the radius of the middle circle equals to 2 units. So CY equals to 2 units, and CD, what is the value of CD? The value of CD, it is actually CO minus DO. CO minus DO is CD. That is to say CO is 2 units and DO is R. So CD equals to 2 minus R. CD equals to 2 minus R, and R equals to 1. So it is actually equals to 2 minus 1, and 2 minus 1 equals to 1. And CM equals to R plus 2. CM, it is the distance between the two centers of the two circles. Therefore, it equals to R plus 2, and R equals to 1. So R plus 2 is 1 plus 2, 1 plus 2 is 3. So we found out that CE over 2 equals to 1 over 3. We multiplied the equation number 2 by 2, and we got that CE equals to 2/3. CE equals to 2/3. CE equals to 2/3, and CD, it is actually equals to CO, that is 2 units, minus DO, that is 1. So 2 minus 1 is 1. So CD equals to 1 unit. CD equals to 1 unit, and CD equals to 2/3. And DE equals to CD minus CE. DE equals to CD minus CE. That is to say it equals to 2/3 minus third. DE equals to CD minus CE, and CD equals to 1 unit, and CE equals to 2/3. So in total, DE equals to 1 minus 2/3. 1 minus 2/3 is third. We found out that DE equals to third. DE equals to third, CD equals to 1, CE equals to 2/3. Okay? Then we focused on the right triangle OEB. We actually proved that the right triangle OEB is a right triangle. Right triangle OEB is a right triangle. Here we have those two angles that they are located between the parallel angles AB and PQ. Therefore, they are equal to each other. And at point E, the sum of the angles from one side of point A equals to 180 degrees. So if this angle is 90 degrees, then this angle must be also equal to 90 degrees. So in this way, we proved that this angle equals to 90 degrees. Therefore, we proved that this triangle OEB is a right triangle. So we can implement the Pythagoras theorem in the right triangle OEB. We have already found out that OE equals to 3 over 4 units, and OB is the radius of the semicircle, therefore it equals to 4 units. Okay, so we implemented the Pythagoras theorem in the right triangle OEB, and according to the Pythagoras theorem in the right triangle OBE, OB squared equals to OE squared plus EB squared. OB equals to 4 units, so OB squared is 4 squared. 4 squared is 16. OE equals to 4 over 3 units, so OE squared will be equal to 4 over 3 squared plus EB squared. So 16 equals to 4 over 3 units. 4 over 3 squared is 16 over 9 plus EB squared. So in total we got that according to equation number 4, 16 equals to 16 over 9 plus EB squared. We subtracted 16 over 9 from equation number 4, and we got that 16 minus 16 over 9 equals to EB squared. Here we multiplied 16 by 9 and then we divided by 9 in order to have a common factor with 16 over 9, and we got that 16 times 9 over 9 minus 16 equals to EB squared. 9 times 16 minus 16 is 8 times 9. So 8 times 16 over 9 equals to EB squared. We know that 16 equals to 2 times 8. So we substitute that 16 by 2 times 8. And we took a root out of this equation number 4. And we got that EB equals to the square root of 8 times 8 times 2 over 9. The square root of 8 times 8 is 8, and the square root of 9 is 3. So in total we got that the value of EB equals to 8 over 3 times square root of 2 units. Okay? Then we actually proved that those two right triangles can go into each other. Why? First of all, the hypotenuse in those two triangles are equal to each other. OB equals to OA equals to 4 units. This is the radius of the semicircle. OE is a common side, it belongs to both triangles. So OE equals to OE. It's a common side that belongs to both triangles. So we proved that those two triangles can go into each other according to the rule that triangle AOE can go into triangle OEB according to the rule that if two hypotenuse and a perpendicular are equal in two right triangles, then the right triangles can go into each other. Whenever you have two right triangles and they have hypotenuse and one perpendicular that are equal to each other, then those two triangles can go into each other. Therefore, triangle AOE is going to go into triangle OEB, and therefore the fact that those two triangles can go into each other, we will conclude that AE equals to AB, AE equals to EB, according to the rule that corresponding angles in congruent triangles are equal to each other. Triangle OE can go into triangle OEB, therefore the corresponding angles, the corresponding sides are also equal to each other, that is to say AE equals to EB. AE equals to EB, and actually, as you can see from the drawing, AB equals to AE plus EB. Again, AB equals to AE plus EB. So we can write here that AB equals to AE plus EB. Okay, AB equals to AE plus EB. But we have already found out that AE equals to EB, so we can substitute AE by EB because AE equals to EB, and we'll get that AB equals to EB plus EB, that is to say AE equals to 2 times EB. And we already found out that the value of EB, it is actually 8/3 times square root units. So we'll substitute EB here by 8/3, we'll put the value of EB inside EB here, and we'll get that AB equals 2 times 8/3 times square root of 2. So in total we got that AB equals to either 16/3 times square root of 2 units, or in terms of numbers, the length of AB is 7.54 units. I will repeat again. The length of this chord AB equals to either 16/3 times square root of 2 units, or in terms of numbers, the length of this chord AB equals to 7.54 units. Okay, thank you very much.